Well, hello everybody. Alright, we have a very, very lively audience today.
Actually, there's no one here for this episode.
Shh. Okay, anyway, let's all give a warm welcome to our guest. Alright, guys? Yeah, any words, Mr. Einsteinberg?
Well, Mr. Okra, let me tell you that it is an honor for me to be here today.
Excellent.
Although I must admit it was pretty difficult to get here, I have a quantum car. Every time I look at the compass, I keep getting lost. But I managed to get here on time, so I'm really happy to be here and join you today.
What?
I'm sure you've heard about about quantum mechanics, yes?
Oh yeah, quantum mechanics, yeah.
Well, you see...
No, I haven't.
Well, you see, momentum and position are non-commuting operators. So, you know?
No, actually. No, I don't know at all.
Oh, well, operators are physical quantities which transform wave functions. All operators have their own eigenstates, a physical state, and eigenvalues, the measurable answer.
Oh, and the wave function is the probability amplitude of finding a system in a certain state, correct?
Wait, so you know quantum mechanics?
Yo, no, bro, no. I'm looking at Modphys notes from Robert and Vamsi right here. They're so good, mind-blowing, man.
And John, too, right?
And John. What the... It says here that commuting operators' quantities can be measured at the same time, but non-commuting operators, they can't be measured. Oh man, dude, I feel so enlightened. Yeah, and in fact, I think you co-authored this book, didn't you? The one right here.
Oh, how nice. Yeah, that looks quite similar. Oh yeah, I'm pretty sure actually this might be the book that... Let me take a look for a second. Yeah, this was the book that I wrote a couple of years ago on modern physics. If I remember right, yeah. So, oh yeah, I wanted to tell you about the Heisenberg principle. Heisenberg determined this with his uncertainty principle, which is an inequality which gives a limit to the accuracy with which the position and momentum can be known simultaneously. That's what the book says here. And basically, what I want to make sure that you know is that this principle states the standard deviation of many identical experiments of both position and momentum multiplied together is greater than or equal to h bar divided by 2. And Planck stated that the energies of light must be integer quantities.
Oh yeah, yo, can I see the book?
Oh, of course.
Oh man, you got some really good modern physics right here.
Yeah.
Wow, this Heisenberg stuff is really amazing. So Einsteinberg, tell me, what do you and your light particle friends do in your free time?
Well, you see, we like to play soccer because we know how to kick a soccer ball near the speed of light, which involves relativity and such. So it's kind of really awesome. And on top of that, we like to play League of Legends, you see. That's a quite interesting game involving light particles. Oh yeah.
What else do you like to do?
Spinning competitions! They're awesome!
Spinning competition?
Yeah!
Are you okay? From what I see, the spinning competitions don't seem like the best thing, huh?
Well, you see, spinning competitions can get a bit rowdy, you see.
Oh, so this is all normal?
Yeah.
Oh.
That's completely. It's our way of interacting. Oh, I gotta get to class!
Article explained the Copenhagen interpretation of the uncertainty principle. Yes.
Well, according to the Copenhagen interpretation, all particles have a wave function. Each particle chooses a position at random, and it's impossible to predict the position of a single particle with certainty. But when a measurement is made, the wave function collapses to what we just measured it to be. We know the de Broglie wavelength equation, which is that Planck's constant divided by momentum gives you the wavelength of a particle.
All true and all good information, but It's a little bit incoherent. I think I'll take it from here, having years of experience as a teacher. Years ago, the double slit experiment and the photoelectric effect experiment were performed. During the double slit experiment, we found that when photons were fired through two slits, an interference pattern is formed. An interference pattern is formed because the trough of one wave corresponds to the crest of another wave. This produces destructive interference because when two waves, you have one wave acting on another wave, you simply add them together. Whereas when you have the crest of one wave with the crest of another wave, you get double the amplitude. So what you have is areas of extra brightness and areas of darkness. This strongly indicated that light is a wave. Because if you do this with, for example, water, you will get an interference pattern, and water, you hit water, it's a wave. However, the photoelectric effect gave very contradictory data. In the photoelectric effect, we found that when you shine a light on a piece of metal, you get an electrical current, but when you increase the luminosity of the light, the electric current does not increase. However, when you increase the frequency of the light, the electrical current does increase. Also, we found that every metal has a stop velocity. Not a stop velocity. It has a frequency at which it no longer will conduct electricity. Any frequency lower than this frequency will not produce an electrical current. This is contradictory to the model of light as a wave, because if it were a wave, it would simply take time to remove the electron from the metal.
Schedule. We have a physical again today.
Hello, I'm the nurse.
Oh God, I hate physicals. You measure our spin and energy.
Wait, spin. You did that before. What exactly is spin?
Spin is the intrinsic angular momentum that every particle has.
Oh.
Alright, that's good. Okay. You need to take more vitamins. Energy of 1.85 eV. It says here that your frequency is 429 terahertz.
Isn't that quite high?
No, it's fairly normal for a light particle. That's in the red or infrared range. Not quite sure. Energy equals h times frequency. So your energy was your energy should be 1.77 electron volts. You're running a fever. You need to take your vitamins.
Okay.
So let's look at your new wavelength now that your energy has changed.
Wait, hold on. What is the H in the previous calculation?
Oh, the H, that's Planck's constant.
Yeah.
Ah, that's right.
Well, your wavelength should be the speed of light over your frequency.
Right.
So your wavelength is 3 times 10 to the 8th meters per second over 429 terahertz. So your wavelength is approximately, because we don't have the exact speed of light here, it's a little bit, a few more decimals. Your wavelength should be about 700 nanometers. So that puts you firmly in the red range. Alright, so now I'm going to test your blood type. To do this, I am going to repeatedly make measurements of the operator B of your wave function. Between measurements of this, I will perform the poop wave operator on you, which does not commute with the blood test operator. But to perform the poof wave poof test, simply you will perform either a boop or a beep, because that is fundamental to your particle. So, I am going to perform approximately 60 billion tests, intermittently doing the poof operator on you, to see if your wave function still matches this. Because you have a fever, sometimes the wave function can change. A. Boop. C.
Beep.
60 billion trials later.
Alright, so an issue arose. After 60 billion trials, we should have gotten data that was approximately but not exactly equal to your wave function. However, when we took the probability, judging by the wave function we had in your file, we found that approximately 1/3 of the time, your blood type will be measured in state B. However, in actual results, over 60 billion trials, it was in fact only 1/6 of the time. This means that you're ill and need to take some medicine.
Yeah, man, that's an interesting life you got there.
Yeah, it's quite a busy one though.
Yeah, quite a busy one, quite a fun one too. But yeah, definitely would be fun to be a light particle.
Yeah, tell me, it's quite fun.
Anyway, dude, great having you on the show.
Man, it was great being in your show. I enjoyed it.
That's excellent. And all right, I guess, ladies and gentlemen, it's over.